welcome back to our course, Fundamentals and Biomedical Application of Quantum Science. We are in the first block of the course where we give in the fundamentals of the quantum concepts. And then we're going to do applications, we're going to generalize, we're going to try to make you understand a little bit the quantum mechanics, and so you can appreciate how important is quantum mechanics in general, in special for bioengineering and many other engineerings. Okay, well, last lecture I explained to you the wave behavior in the atom, or in any physical system that we could apply. We put the angular momentum, but angular momentum like in the Bohr atom. You know, Bohr proposed angular momentum because he knew that things are orbital. He proposed a model for the atom, and he explained the atom. And then we saw that all the hypotheses of Bohr, when he creates the ideas, he quantized the angular momentum. He made the angular momentum be an integer number of h bar. This is what we call quantization of the angular momentum. But you know, many physical systems, they do not have angular momentum. Like the harmonic oscillator. That means that I can only calculate, if we look for Bohr principle, we can only calculate the energy of an atom of a single electron. We needed to generalize this. I told you in the last lecture that now we have to somehow go generalizing a little more the concept so we can create an equation that is valid for any situation. Okay, so now comes another great contribution, and is a step up from Bohr, which is, we know that Bohr, he explained how to make a discrete set of energy for the one electron atom, quantizing or imposing that the angular momentum cannot be any value. It has to be an integer number of h bar. And then we went there, in a smart way, we find out that that represents waves, de Broglie waves being accommodated on the conditions of the orbits. This is a very important thing, because basically quantum mechanics is accommodating the wave inside the physical conditions, with the boundary conditions we have. Right? And much before we learned the Heisenberg principle. So, you know, following Bohr ideas, we obtain all the energy of the one electron atoms, what's very good, and then we could explain, right? Now, Summerfeld, he gave it one step further. He said, well, that may be generalized for a system that does not have angular momentum. Angular momentum is a special conditions for when we have orbit. So then Summerfeld said, if you have a periodical system represented by momentum and position, periodical means a system that repeats in time. You know, we may reach the same condition because we don't know how to deal with those waves yet. We don't have a master equation. You see that we're speaking about energy without speaking about wave function, right? We are drawing waves and everything, but we didn't reach what we need. But Summerfeld said, well, look, if around one trajectory of the particle in any periodical conditions, 1, 2, 3 dimension, if it is periodic, and this integral symbol means that I have to integrate in a full cycle. So this is a full cycle, right? So if I integrate in a full cycle, the momentum and the position, I must have an integer number for h. And that's somehow generalized Bohr, because if this is in an orbit, dx will be basically, right, will be 2 pi r, right, 2 pi r d theta. If I have an orbit, maybe this is worth to show you. So if I have an orbit, I have a particle that's going around. So the dx now is tangent to the trajectory. So this is my dx in my integral. The momentum is here, the particle is going around here. And dx is nothing more than r times d theta is dx. So this integral became p r d theta. And the only thing that's varying in an orbit is d theta, that it gives you 2 pi. So I get that pr, which is the angular momentum, times 2 pi is equal to nh. So I get that the angular momentum times 2 pi is nh. Or, divided by 2 pi, angular momentum is equal to nh bar, because the h divided by 2 pi is h bar. So the concept of Summerfeld involve is more general than the situation of Bohr. And we are looking for generalization, so we can treat any problem we want to obtain the energy spectrum, to obtain the conditions that waves fits in that geometry, in that physical system. Okay, so basically Summerfeld said, look, for any periodical system, this is the condition for stationary waves. And Bohr orbitus is just one case of this. Let me apply this for a few physical situations where you may appreciate to see what's happened. And the first thing I'm going to apply is the particle in a box. Why we like particle in a box, harmonic oscillator? Because many things in nature are like that. You're going to see that macromolecules, we have macromolecules in biomedical, right? And if the electron is delocalized, it's like a box. You know, we're going to be able to obtain energies. We're going to be able to obtain why some molecules have specific colors just by looking at the delocalization of the electrons in this contest. Wait to see. Okay, but we're going to consider the particle in a box. And considering this particle in a box, we know that the particle comes and goes in periodic motion. The energy is given by E equal to P squared divided by 2m, which is the kinetic energy, only kinetic energy here. This is a rigid wall. There is no penetration of the particle. And the particle comes from minus a over 2 to a over 2, just to be symmetric. When the particle is going on the positive, you know, P is equal to 2m root square times E, 2m E root square. So this is when the particle is going in the positive direction. When the particle is returning on the negative axis, is minus. It's the same thing minus, right? So we have the P. If we draw in the px diagram, we have here when the particle is coming, the value is minus root square 2me. When the particle is going, is root square 2me. And we learned from Summerfeld that we have to integrate p dx. Integration of p dx in a px diagram is just the area confined by the trajectory. Is this? This area here is the integral of a full cycle. And this area for the full cycle, which is the area, right, is A, which is the basis, times 2 root square of me. And following Summerfeld quantization rule, this has to be equal to this, to NEH. There is no pi here, there is nothing. It's fully different from the Bohr atom. It's a different situation, but he showed that this is more general. And I'm going to explain what Summerfeld was thinking. Right? But he found a relation. He found a way that we do the mathematics to obtain the energies of a quantum system. This is the main value of Summerfeld relation. So, if we take that relation that we saw in the last page, 2a root square of 2me equal to NH, we just square this relation and obtain that the energy is equal to n squared, and n can be what? 1, 2, 3, 4, and so on. Right? We obtain that the energy of the particle that's confined by a length A goes as n squared, h squared, everything that's quantum will depend on the Planck's constant. You have to learn that from now. Divided by 8ma squared. The lowest possible energy is this, which coincides with the Untitled Principle for this case. If you look there, it coincides. There we use L, but L was 2A. So you have to, when you substitute this, you find the 80 here. So there is a lowest possible energy. The lowest possible energy is the fundamental state, or the fundamental energy, the energy of the fundamental, which is this number. A particle that's confined by A cannot have energy lower than this. Let's take a look on what is behind the Summerfeld Principle. And you know, what's behind is that what he's doing, he's matching waves in this box. He said, well, the first wave I can put in this box, remember the size of the box is 2A. No, it's A, right. We went from A minus A over 2 to A over 2. So minus A over 2 to plus A over 2. This gives us a length of A. So the first wave, de Broglie wave, lambda equal to H over P that I can put here, is when lambda, because, when you put a wave in this rigid box, it has to go to 0 because the particle cannot exist beyond this point. Cannot. So it has to go to 0 here, the wave that represents the particle. And the best I can do is put a wave that half a wave is the total length available. And if I combine this with this, so lambda over 2 is equal to A, and I put in here, I get P, and then I get P squared divided by 2m, I get the first energy. So actually, the Summerfeld relation is providing us how waves can fit in that geometry, how stationary waves for these localized particles that are in periodic motion can be there. Now, what is the second wave we can put? The second wave we can put is when we have a full oscillation. That's the second wave. And then lambda is equal to A now. And then P, the momentum, is H divided by A. And the energy, of course, is H squared divided by 2ma, which is exactly this relation with n is equal to 2. And so on. What is the third wave that we can put in here? Well, the third wave is when we have 1.5 oscillation, which means that lambda plus lambda over 2, which is 3/2 of lambda, is equal to the size A. Therefore, we get the momentum, and therefore, we get the particle, which is the energy when n equals 3. 9 divided by 8 times h squared divided by ma squared. So you see, what Summerfeld has done is a condition that led us to find the relation between momentum and position, and that provides the energy, because the energy is from momentum and energy. In this case, momentum is constant in some space, but we can find another example for you. I solved the harmonic oscillator for you there. Now I'm gonna solve the harmonic oscillator here. So the box is easy to fit waves because the boundary is rigid. It's like the wave in a string, right? Like a resonant wave in a box. That's easy to do. Now, when we have a harmonic oscillator, it's not so easy because the boundary condition is soft. The energy of the particle in any point of space is the combination of the momentum and the position. And it's not so trivial to draw a wave in here. But the Summerfeld relation have that. The Summerfeld relation knows that the wave cannot die here because it's not a rigid wall. It goes a little bit beyond the potential. Now pay attention. We're going to take this. We want to find what is the values of the energy, which are the energy levels, or the energy available from the quantum point of view for this potential. So we must just go on with the Summerfeld. Will be my last application of Summerfeld. Now I can take this expression. I can divide everything by E, right? So I'm going to rewrite this expression following this. I divide by E, so this is 1. And then I have P squared divided by 2ME. And here I have X squared divided by 2E divided by M omega squared, where omega is the frequency of the oscillator. If we put a particle here, it will oscillate with that frequency, classically speaking. Now, what Summerfeld told us is that you have to integrate. You have to take the integral in a full cycle of P dx, and this must be equal to an integer number of h. The easiest way of doing that is drawing in the px space the whole trajectory. But turns out that this is the equation of an ellipse. This is an elliptical trajectory in the px space. And the integral in a full cycle, again, is nothing more than what? It's nothing more than the area of this trajectory. And we know the area of an ellipse, right? And the area of the ellipse must be an integer number of h. So the integral of p dx is p times the one of the what they call the semi-axis times the other semi-axis. And this, you know, if you remember the equation of the ellipse, this is one of the x's square, and this is another x square. So the root square of this give us this dimension here, either the long or the short semi-axis. Right. So this is the long semi-axis, this is the short semi-axis. And I guarantee to you that root square of this guy here is this distance here. Easy to prove. And root square of this is this. And this times pi is the area. And that must be, so pi times this, which is the 2x's, equal to NH, following the principle of Summerfeld. Therefore, if you multiply, forget about this, we get that the energy must be an integer number of h bar omega. Here we have to scale, we have to allow n to be 0 because we're gonna add explicitly the energy of the ground states that we calculated before. So the energy for a harmonic oscillator is n plus half times h bar omega. And of course, most part of this, not total, the any part, we obtain by Summerfeld relation, which is the integration. So everything we're doing here is basically matching waves in the physical geometry. Physically, what we do, when we say that we have a physical system, we have a potential with a massive particle. This is what we're doing, right? And by doing this, in this situation, we are trying to find how can we calculate the waves that are there. And not always is easy to map. Sometimes it's hard to map. And then what we do is we go and we use the relations that people find out to be true. Now, this is the potential. And let me tell how the waves look like. We're going to solve this after getting the equation. One wave looks like this. The other wave looks like this. And the other wave looks like this, and so on. We could draw those waves by hand, guessing that that's how we match waves in here. But we still need an equation for doing this. And that will be the main thing of the quantum mechanics, is make sense of the equation that we're going to obtain. That's called the Schrödinger equation. Okay. So, what we learn in this lecture? We learned in this lecture that we gave one step up in finding out how are the energies of a confined system that are periodic. And we use a relation that we don't know very well. You know, Bohr proposed a relation. Summerfeld generalized this relation. Everything seems to be working fine. And we were able to calculate that the energy is discrete. Depends on the number that we call quantum number. So those numbers here, in any of those cases, those numbers are called the quantum number, right? So those are the quantum number, because they are numbers that appear because of the quantization of the energy. Oh, here I did the ground state, the minimum energy, and then I add up. That's why I start in 0, not in 1. Right? Okay. So, normally what we're doing is to see how a de Broglie wave can be matched in some physical situation, which is described by a potential or something that confines the particle. And that provides the energy, you know. And because waves cannot be put in there in any way, there are a few waves. It means we end by a few relation between momentum and position. Therefore, we end with a few energies. That are the energies of your system. So, but I draw, and you trust me, how the waves in a harmonic oscillator looks like. But actually, we don't know. We never, you know, waves in a box is easy, but waves in a harmonic oscillator is not easy. We just draw there by, you know, waving hands, but we didn't obtain anything. We did not obtain any wave function. We must have wave function, and we must have to learn how to get the wave function, and from there, extract everything. The energy is everything. All the behavior of the system has to be there. At the moment we are creating and observing that the wave mechanics for the quantum world is necessary. But we didn't get the equation yet. We don't have a master equation. We must obtain the way we can, or we must understand how a wave equation can be proposed. And we're going to start to do that. I consider that now we are getting out of this block of the course where we should understand how people construct the ideas of the quantum concepts. And now we should be able to elaborate a little more to apply for some systems, right? But you already understood that we are dealing with waves, and waves of matter. We call that way, but we don't know waves of what. Not like the electromagnet. We cannot say they're waves of mass, that mass oscillates or anything. We have to give an interpretation for this wave. But we need also the master equation, right? We cannot keep going with propositions. We know, we accept already that wave is the right way to describe electrons in atoms, confined particles, everything around us. Even if we cannot observe. That's the right way to describe. But we needed to evolve on that, right? We cannot solve complicated problems if we don't have a master equation. If we don't have an equation that's englobe all the concepts and give us the solution. So in the next lecture, I'm going to explain to you how can we get this wave, and then finally, what is this wave made of? What is our interpretation of this wave? How can we use this wave to obtain all the physical properties of any system? But at this moment, it should be clear in your mind that we accept that we have to treat the physical systems as waves. That's a way to determine the right properties. I put many examples, the spectral lines, the radiation. So what I did up to now in those lectures was to construct the concept, because the idea of this course is to construct the concepts, and then we apply. And then we understand what the observation is showing, and the interpretation based on the quantum concepts of those waves. Okay, thank you very much. See you next lecture in the same place. Bye-bye.